Next, we have anti-reflective coatings, and this is where Brewer Science contributed to the history of lithography and moving the industry along. It's not like the anti-reflective coatings on your sunglasses, but this video will help explain.
So why do we need anti-reflective coatings? During the exposure step of the lithography process, any light that passes through the photoresist can be reflected by underlying layers. In earlier generations of the photolithography process, the patterns being formed were much larger, so reflections from the underlying layers were not problematic. In today's advanced processes, where feature sizes are measured in nanometers, these same types of reflection would ruin the patterns in the photoresist. In some cases, reflected light from the exposure bounces up and disrupts the incoming light, causing an interference pattern known as a standing wave. As its name implies, a standing wave will create an undesirable wavy profile along the walls of the exposed photoresist. Reflections become even more problematic when patterns must be created on top of existing structures. These various peaks and troughs can reflect the light at different angles, resulting in a phenomenon known as reflective notching.
Back in the 1970s, the photoresist patterns were big. I mean, microns. You could probably draw them with your Sharpie marker. And that was okay. Diffraction, reflection, other optical issues really weren't that big of a deal. But as they started getting a little smaller, it started causing trouble. Some chemists tried to solve these problems, making some sort of anti-interference phenomena, or let's make that resist non-reflecting. Well, that's kind of a problem if you need the light to get down into your photoresist to do something. And so that's probably not the best way to go. All of that kind of reflection causes something called standing waves. Here's a good example of what's going on. We get really wavy profiles. Well, they look cool, but they're bad. This can cause, like we can see like here at the bottom, if it catches that way, that line can get a little wobbly, could topple over. If you're trying to deposit something in here, that could get in the way. It leads to problems. And so we needed something to help solve that. And if you remember, this wafer is really, really, really shiny, and that's kind of the source of all our problems. That light is just coming back off and causing trouble in the photoresist. So how do they work? So Barks, kind of I'll oversimplify the physics here. If you guys know physics, you probably know more about this. But so Barks work by inherently just reducing they're absorbing. So they absorb a lot of light. And we use optical characteristics to do this. So we use the refractive index, the imaginary part, and thickness are all important factors in controlling how much of that light it captures, how much it lets bounce back out. And so those are kind of factors that we use. But with this property, they just induce a phase shift component that basically destructively interferes with the incoming light, gets rid of the standing waves.